This is an infomercial for 3D Fuel PCTG filament, and most of its screen time will show it failing. I do endorse this product, but I didn't realize they made it at the time. This is going to be a weird episode. Everyone seems to forget that a 3D printer is a physical object that makes physical objects out of other physical objects. And the thing about physical objects is they're affected by physics. I'm talking fluid dynamics, thermodynamics, even Boston dynamics. The robots are taking the robots' jobs. There's a whole universe of chemistry quirks, physics phenomena, and mechanical misfortunes itching to trash your prints in ways you never even dreamed possible. I mean, you might have. I'm just a grid of flickering conflict minerals drowning out the intrusive thoughts of your lonely death until you're done pooping. I don't know you. Ladies, gentlemen, and cyborgs, I'm your host, Zack Freedman, and this is Void Star Lab, where today we ask the big questions. Questions like, why did this print fail? Why did this print fail? Why did this entire spool fail? I will describe a problem in detail, then I'll give you 3 clues, and then finally I will reveal the truth. And I'm gonna make it all very obviously telegraphed, so you can pause if you need time to think. It's like a murder mystery for makers, and you're the schneefed up detective. And before you just skip all the clues, cause real men always play in hard mode, I didn't say hints, I said clues. Most of these situations are so subtle, rare, and complex, I struggle to even get them on video. But not this one. Let's ease ourselves in with today's easiest mystery. Once upon a time, I cracked open a fresh spool of nylon filament and ran off this telescoping fork so I could sample my wife's desserts for quality assurance purposes. It was almost immediately destroyed in circumstances unrelated to this puzzle, so I hit reprint. At this time, it came out all stringy, blobby, and raggedy, and the layers were so weak it practically collapsed under its own weight. I tried again, and this time the print almost immediately turned into spaghetti. You already know the answer? You don't even need to hear the clues? I haven't even finished describing the problem. I too am smart, so I recognized the signs of waterlogged filament and I threw my nylon in my filament dryer, along with some super hard polycarbonate, aerated PIBA, liquid crystal polymer, twisted triple co-extruded silk PLA, and cannabis scented TPU. The next every filament episodes are gonna be buck wild. Here's the real issue. When I put the nylon back in the printer, the filament practically crumbled. It was so brittle and so fragile, I couldn't even thread it into the feed tube, let alone have it survive the epic voyage from spool holder to hot end. Prepare to pause if you think you have all the information you need, because I am about to deliver your very first clue. The other filaments in the dryer still work perfectly. Only the nylon is doing whatever the hell it's doing. Get ready for your second clue. It was Magic the Gathering night at Den Hack, and then it was Double Affinity weekend on Warframe, and then I had some beers, and then I kind of maybe dried the filament for a few extra days. The final clue is as follows. This problem seems to have solved itself. I tried the filament again, and now it's just as flexible and it's working perfectly. I didn't do anything about it. Printer problems are so scary to me, they solved themselves. That's not really what happened. But what did? Give it a good mulling over, think it through, and hit pause if you're a particularly thorough brainiac, because I'm about to spoil the answer. Just like I spoiled my nylon by drying it way too much. But then why didn't that ruin the other filaments too? Because those filaments are not nylon. Polyamide is one of the very few polymers that are strengthened by water. Why did I put R? That's so weird. The more moisture nylon absorbs, the tougher and more flexible it becomes. Everyone knows you have to dry nylon before and honestly as you print it. But if you go too far, the plastic actually stops being plastic. The solution is to simply leave the spool exposed to air until it drinks enough dihydrogen monoxide to get its groove back. You can actually strengthen nylon prints by dunking them in water. I chose this as our first puzzle to illustrate that while all filaments are subject to the same laws of physics, some respond more intensely or idiosyncratically than others. Here's my favorite example. PCTG, an advanced cousin of the more common PETG, and one of only 6 polymers that I gave an S rank on my 3D filament tier list. It's mechanically superior, it's precise and stable, and you can print it almost as clear as glass. It can even be made more colorful than most other filaments. However, minute changes to your print settings, to the printer itself, and even the room the printer is in can make PCTG behave wildly differently. Especially when it's from this video's sponsor, 3D Fuel. They actually made the exact filament that I put in S tier. That reel was branded Essentium, which was an industrial printing supplier that went out of business around that video's air date. Well, imagine my surprise when I got an email from John Schneider, CEO of 3D Fuel, who said they had made that PCTG in the first place. That exotic deep-cut pro-grade esoterica I had to special order from Italy was actually manufactured in Fargo, North Dakota. Other manufacturers cut their PCTG with other polymers so it's easier to print. But like, you don't buy PCTG because you want PETG. 3D Fuel's formula is pure and uncompromised. They trust you to take your printing seriously enough to dial the stuff in, and the reward is an all-around superior filament. The chemistry that gives PCTG its strength and precision also makes it notoriously viscous. It's gloopy and sticky, and it doesn't like moving around. Plus, it's glossy and transparent, so if a defect makes it into your print, it's got nowhere to hide. That's why I'm going to use 3D Fuel's PCTG to demonstrate many of today's printing problems. Problems that, to be absolutely clear, other filaments absolutely have. You actually can print PCTG absolutely clear, but I'll pause my ADHD long enough to point out the infomercial disclosure was required by the FTC because I'm going to heavily feature the sponsored product. Not just because I'm a huge shill, but because it's really good at demonstrating esoteric printing problems. Visit the link in the description and take the PCTG plunge. If you know what to look for, you can tame any filament. That's why we're here, to help you develop an eye for trouble. It's time for our first 2 3D printing challenges. That's 6 dimensions of challenge. Weak layers, matte surfaces, tiny bubbles. They're usually telltale signs your filament got wet. Usually. PCTG is nearly waterproof, except these 2 PCTG prints have all the symptoms. These issues are actually caused by bad slicer configurations. The one on the left has a single setting too high, and the one on the right has a different setting too low. It's time for some double bubble trouble. I thought that was very clever. We're going to start with the left one first, and I'm going to give you a free clue to focus your wild guesswork. I mean your thoughtful deductive reasoning. This was caused by PCTG's most notorious trait, which you missed if you skipped the sponsor plug. Prepare to pause, because here comes your first real clue. The setting in question has a unit of millimeters, and you can find it in filament settings and printer settings, maybe even on the printer itself. Your second clue is this. These are air bubbles, and they enter the system through the nozzle. And here's your final clue. When I swap my printer's high flow nozzle for a regular nozzle, the problem is significantly but not entirely reduced. Consider this your last chance to pause and review the evidence. Okay, time's up. This is what happens when you suck air into a highly viscous filament, and the problem setting is retraction length. Molten filament likes to dribble, so we tell the printer to reverse thrust and empty the nozzle when it's not supposed to be squirting. But I increased it too far, and now air is getting drawn up into the molten filament. Told you shit's getting weird. When a fluid starts flowing, it doesn't all flow at once. The center starts moving while the edge stays stuck to the walls. It's called the shear rate, and the more viscous a fluid is, the longer it takes the outermost layer to get rolling. Occasionally, because of shear rate, some liquid pulls loose, and that closes around the air and entraps a bubble. The bubble stays stuck in the fluid because, again, the fluid is very viscous. It's even worse with a high flow nozzle that forks the filament into multiple paths. More surface area does heat more filament at once, but it also provides more square millimeters for sticky viscous filament to plaster itself to, detach from, and capture air bubbles. I already said entrap. When we de-retract and resume extruding, those bubbles get churned into the print line, and they look an awful lot like absorbed water boiling off. To remedy the issue, we simply reduce our retraction distance, and that just prevents more air from getting into the nozzle. This isn't a chemistry issue, it's a mechanics issue. Our final bubble struggle is oddly consistent. This PCTG print's outer perimeter is pockmarked apparently at random, while its inner perimeters and infill look nearly perfect. It's really a shame, because otherwise the print is incredibly clear and glossy. This issue is caused by a single print setting being far too low, or more likely, a different setting overriding that setting with too low a value. So what do we pump up to deflate these bubbles? Let that one percolate, and if you need more info, prepare for clues. Your first clue is somewhat funky. You can't trust your eyes to catch this one, but the nose always knows. Your second clue is as follows. As far as I know, only 3 thermoplastics will do this in normal printing conditions. PCTG, polypropylene, and a third and final polymer that this phenomenon renders outright dangerous to turn into filament. Here comes your third and final clue. You can predict this problem in the print preview screen, but only in a specific color scheme. That means either line type, speed, layer height, line width, flow, or layer time will highlight the potential for this problem. That's all the info you get to pop this befuddling bubble, so pause now or forever hold your peace. This is a really weird problem. This filament is burnt. It doesn't look like it could be true, but hear me out. It overheated so severely, some of its very molecules broke apart, vaporized, and formed gas bubbles that got trapped in the filament. I want to be clear here. That was a pun. We don't want to reduce the temperature. The temperature is how this print got so clear. You're better off solving the problem for real instead of just dealing with the symptoms. The bubbles only appear on the outer perimeter because those are the lines with the slowest print speed. Those are where the filament spends the most time cooking in the nozzle. We have to increase speed, specifically outer perimeter speed, to get the filament out of the nozzle and under the part cooling fan before it can take too much damage. But be aware, simply cranking up the print speed might not actually change anything. Minimum layer time and volumetric flow limit will both override the nominal print speed. So if you're printing a sensitive filament, remember to check the print preview color-coded by speed to make sure the slicer isn't going over your head. PCTG is especially vulnerable because of that last letter. The glycol in polycyclohexylene dimethylene terephthalate glycomodified is CHDM, the same additive that puts the G in PETG, and it boils at 285 Celsius. The reason you don't have the same problem with PETG is because you usually print that at 240, but if you want the strongest, most transparent prints, you'll print PCTG at 280.
Boo, you hack! 280 is lower than 285.
They're throwing math at me.
Wait, don't eat me! The peanut gallery is only a figure of speech! No!
Chemical reactions still happen below the nominal critical temperature. They just go slower. That's why you don't want that filament loitering in the nozzle even a half second longer than necessary. Polypropylene is actually even worse because it starts decomposing at its melting point. Your nozzle can start visibly smoking while you lay down the pee-pee. You don't usually have to worry about this because the main byproducts are carbon dioxide and water vapor, so the third and final printable thermoplastic that smokes like a 50s housewife is PVC. Yeah, that's right, the plumbing polymer that surgeons just love removing from people who build potato cannons is a thermoplastic. However, it's a thermoplastic which, at PLA printing temperatures, can release chlorine gas that forms hydrochloric acid inside your lungs. I actually found a PVC filament called Filamentum Vinyl 303, and I was going to put it in my Cursed Filaments episode. I ended up cutting it at the last minute because PVC pipes are extremely common project materials, and I don't want anyone hearing PVC as a thermoplastic unless it's immediately followed by hydrochloric acid inside your lungs. Keep your nose open because if it smells noticeably nasty, there's probably a problem. Okay, enough bubble puzzles. Your third challenge, there's a fourth? How are we counting these? Is something I've dealt with myself, but years and years ago. I honestly thought modern printers had become immune to it. But John from 3D Fueled said otherwise. It is a frequent complaint from certain users of certain printers who just bought their first reel of a certain filament. It's PCTG. The filament is PCTG. This print walls look crisp and clean, but the top surface is a totally different story. Chunks of the very top layer are muddy, nasty, and shredded, almost like this print lost a fight with a cheese grater. What's weird is the whole plate is scattered with tiny crumbs of filament, hundreds of them. A few have even been kicked all the way into the printer's chamber. The solution is on the printer's touchscreen. I don't have to reslice the model or mess with config files. I could, but a single finger would actually solve this faster and more smartly. The smartliest. This one is so bizarre, my first clue is going to straight up give away what made these crumbs. It's only a symptom of the true problem. Feel free to pause if you think every game should be Dark Souls, because here it comes. The top surface went all f***y-wacky because the nozzle got slightly tilted off axis. The edge of the tip is digging into the print like a tiny plow, scraping up the filament and rolling it into little snowballs. So why is the nozzle tilted, and why is it just happening on just part of just the top surface? Here's the second clue. Pause if you need to pull up a dictionary to look up the following vocabulary word. I exacerbated this issue by making the top layer's infill run parallel with the y-axis. It's less prominent at the normal 45-degree angle, and it's basically gone when the top infill runs parallel with the x-axis. And as for your final clue, you actually get a double bonus clue if you watch the last episode. The only machines I can actually reproduce this on are my oldest printer, a Replicator 2, and my newest printer, a Voron Trident. I could possibly trigger this on my Pantheon HS3 or Bamboo X1C, but I would probably have to tamper with the hardware and firmware. Now don't let my nozzle tilt make you tilt. Why did I say it like so weird like that? Why did I say nozzle? Nozzle. Pause the video, find inner peace, see if you can guess why, the how, the what, the what. Time's up. Our tumbling filament tumbleweeds are indirectly caused by a moment of inertia. Like inertia is to motion what a moment of inertia is to torque. It was applied when the gantry switched direction too aggressively. The solution is right here on the printer's limit screen. We just drop the maximum acceleration and the problem is gone. When I said the specific printer was relevant, I was kind of burying the real clue in unnecessary information. This can happen with any printer that has a top-heavy extruder mounted to a moving gantry. This arrangement puts far more mass above the crossbar than below it, so if the gantry starts or stops too sharply, inertia will apply torque that momentarily and imperceptibly tilts the carriage and thus the nozzle, so its very tip shaves the top off your print. That's why this is so much worse at the edges, because by the time the nozzle reaches the center of the print, it's stopped accelerating and it's returned to its full upright position. The printer's default settings will not actually let the carriage button hook this sharply. I had to mess with printer.cfg to raise the limit. Many makers will raise the acceleration limit to get prints done faster. This is why it only happens with certain makers with certain printers. This is especially bad with PCTG because it loves sticking to itself. This is a surprisingly common issue on Core XY and gantry printers, but it never happens on bed slingers or deltas because their x-axes can't apply that moment of inertia. I used to battle this constantly on my MakerBot replicator too, which I just did an episode roasting. It took literal years for them to release a firmware update that added acceleration. We can't stop, we have to slow down first. Bullshit! Our fourth stumper is a case of missing gear. There's a fifth stumper. I still haven't decided how I'm going to number these. I bought this reel of filament last year. I ran off a single benchy and I threw the rest on my rack to save for later. But when I reached for it last week, I discovered it had spontaneously shattered into short pieces just a few inches long. As I tried to unwind it, it just kept crumbling and snapping in my hands, and it was only the very center of the spool that seemed to have any structural integrity. I could have completely prevented this with an accessory that I could make, buy, or just jank together for like pennies. What happened to this filament, and what's the accessory? Here's your first clue. This filament is a proprietary blend of PLA, but that's not actually relevant. The same thing will happen with any filament as long as it's not very flexible. Your second clue is a closer look at the broken pieces themselves. They aren't brittle. They're just as tough as the whole filament used to be. You can even see the hairlines where it's about to break, and it only breaks there. Your final clue is going to turn this into a multiple choice question. The solution is either a clip to hold the loose end of the filament, a dry box to shield the filament from humidity, or a tinted pouch to block ultraviolet rays. Consider it carefully. How could I have kept my spaghetti in a single long piece, a la the Lady and the Tramp? Last chance to pause, because here comes the answer, and you are not gonna fucking believe it. This could have been prevented with a filament clip. When a manufacturer winds filament onto a spool, they do it while the plastic is still hot, and then they cool it very, very slowly. This anneals the filament, or relieves the stress of twisting the polymer into a tight spiral. It basically causes its molecular structure to remember the new coiled shape as a sort of default. When I printed that benchy, I loosened the filament, and that created internal stress as the polymer tried to return to its tightly coiled state. But it couldn't move because I had looped the free end of the filament through the retainer hole on the spool. Yeah, you can apply strain to filament by leaving it loose. Over time, the stress concentrated in weak spots, forming hairline fractures and slowly prying them open. This only affects rigid filaments because the molecules in a flexible polymer can relieve the stress by slipping past each other. Even my custom filament holders on my rep rack cause reels to spontaneously collapse, which is why I've never released them. It took me way too long to figure out why this was happening. Instead, you want to rewind the filament as tightly as possible and fix the free end onto the windings themselves. The cheapest way to do this is to just wrap the filament in a strap, some string, or plastic wrap, just not a rubber band, because the chemicals in that can react with the filament. If you thread the loose end of the filament through some kind of thin object like a card, it won't be able to tie itself in knots. Here I used a purge tower from a failed print. A more permanent solution is to print a filament clip, but not just any filament clip. Most of these hold the loose end against the rim of the reel, which keeps the reel tight, but it stresses the tip. Remember, this straightened out part is going to eventually snap and let go of the filament. So instead, I recommend the screwed up filament clip by Zombie Hedgehog, a friend of the channel who sent me 6 entire reels of his special blend red filament for no discernible reason.
Friendship!
Get the f out of here. His screw down design clamps the free end of the filament barely 2 millimeters above above the reel and it helps keep it in its natural non-crumbling state. It might seem weird that you can protect filament by pulling it tight, but if it wasn't broken when you got it, it won't break if you store it in the same conditions. Our fifth and final filament focus scenario, or our sixth scenario, is less a problem and more a fun trivia question for a very specific definition of fun. These three models were printed in three different filaments that all share something in common. And it's not their plastic, you bonehead. These prints were really hard to actually finish, but they're insanely rugged, they resist abrasion, they shrug off impacts, and they withstand heavy loads. They even have above average temperature resistance. They're translucent, but they all have regions that are more clear or cloudy than the rest of the print. So what do these three filaments have in common? Here comes your first clue. You can buy versions of all three filaments with additives that make them physically weaker but much easier to print. Now for your second clue. Their physical properties change drastically depending on the print speed and the part cooling fans. With low fans or low speed, they're more clear and they warped more. With high fans and high speed, they're weaker and they warped less. That's right, turning the fans off and printing slower makes these warp more. Here's your final clue of your final puzzle. These filaments are PET, polypropylene, and PEEK. Now's your time to hit pause and chew on it. What makes these filaments special? The answer is, these three filaments are semi-crystalline solids. When any liquid solidifies, its molecules will either freeze in random positions, amorphous, they'll fall into a repeating pattern, a crystal, or they'll end up somewhere in between, semi-crystalline, with chocolate chips of regularity in a cookie of chaos. The way it's printed and cools determines how amorphous or crystalline it is. When we printed these filaments with fans low and speed slow, we gave the polymer plenty of time to stay liquid and form crystals. This made it stiffer and more transparent, but it forced it to warp out of shape. By cranking that hog, we forced the molecules to stay in the same random orientations they left the nozzle, which left the print more amorphous. Crystallizing matter makes it massively stronger, stiffer, and more resistant to heat. The trade-off is, first off, heat resistant is not always a good thing because that also affects the printing temperature, but crystals are dense. Crystallizing a solid actually packs its atoms closer together. It's sort of like how you can fit more oranges in a crate if you stack them neatly. Shrinking your filament mid-print causes it to scrunch up. That is what we call warping. Common filaments print at very low temperatures, so they just solidify quickly. But they're also packed with chemicals called plasticizers that disrupt the formation of crystals. That slashes the strength, but it brings the warping and printing temperature down to manageable levels. You can easily see this when we put the semi-crystalline filaments next to their modified counterparts. This PET has been reacted with the plasticizer CHDM to form PETG, basically the second most common beginner-friendly filament. This polypropylene has been dosed with pigments and bubbled with gases that force it to form smaller crystals. So even though it's still semi-crystalline, it behaves more like it's amorphous. As for PEEK, this is an ultra-high performance polymer because of its semi-crystalline structure, so it's almost always used in its pure state without any plasticizers or additives. I am frankly stunned I managed to print this at all. Semi-crystalline polymers are the most sensitive filaments. My finger quotes 0% fan polypropylene test is actually more warped on one side because the heat breaks cooling fan leaked on the other. When you hear crystal, you might think crystal clear, but it's actually the opposite. The cloudy patches are the ones that have crystallized and the transparent regions are more amorphous. It's due to quantum bullshit I'm not even going to try to understand, but the point is you can clearly see this on the PEEK because it's supposed to print as opaque as a brick. My printer wasn't up to the task, so the filament didn't get hot enough and stay hot enough to crystallize properly. That's why it's transparent. As for polypropylene, that's actually an anomaly that gets more clear when it crystallizes. PP is just weird. And those are 5 or 6 printing puzzles caused and solved by actual science. How many could you guess? I mean, diagnose. Do you have a baffling print problem or a little known bit of trivia that I could feature in a future episode? Head to the Discord and post it on this board, or let me know in the comments below. I'm a poet and I didn't realize it. I'd like to thank 3D Fuel for sponsoring this episode, suggesting some of the more obscure problems, and providing PCTG to demonstrate these rare complications. Links are all in the description. I have never done anything remotely like this episode, and it was pretty tricky to research. I can take these kind of risks and put in this amount of time because of Voidstar Labs patrons. Become a patron and help me drown out the brain dead dead AI garbaggio in thoughtful handmade garbaggio. Each video, I thank 3 random lab scientist supporters, and the chosen ones are Mike and Katie, Jack Matheson, and it's just a period. Or maybe a dot? The only one who knows is. Give it up for our supremely generous collaborators, the most based connoisseurs of bad puns and silly projects in all the land. They go by Schleppy the Schwagster, SXP, Zachary Volpes, Chuck Me Harder Baby, The Benevolent Misanthrope, Gridfy.cc, The Suits Are Our Fun, Turner Zay, and Scott Rini. Tickling the Rini. I've hidden their names somewhere in this video and made them permanent parts of the workshop. Finally, our lab assistant supporters. They're the wind at my back, the apples of my eye, they're the fire of my loins. Platonically. We're just friends. Their names are also quite long and I have to shorten them or the algorithm will steal my kidney. Thank you, Walrus, Michael C., Evan, Clayton, Keymau, Viwatch, Moonkin, Captain Helmet, Max Luck, The Krollster, TR Fullheart, Make Fascists Afraid Again, 6A, 6F, Leaky Heater, Sir Squeaky, Shane, William, Quantumly Tangled, Kathy and Brent, Dr. Lucifer, Slippy, Eddie, Not Raccoon, CCH, Kermit, Not Prince Michael, Haley, Iron, Renaud, The Cune, Lydia, Robert, Lion Cat, Lost Dryer Socks, Pilgrim Labs, Scroto, Sarah Clancy, Nuclear, Bryn, Cowcaball, No Disassemble, Callsign Carrot, Bill Moore, Right to Repair, and I think I ran out of battery. No! Blammo, Achalia Makes Sax Say Trans Rights are Human Rights, Rye Rob, Alfinger, Cookie Cattle Dog, Anti-Tux, Robert, Bill, Quality Doggo, Deorbital, Wuhan Express, Melvin 2001, Michael, Nova Ren, VK, Burrenduck, Agent Maxwell, PRD, Onyx Plague, Travis H, Travis P, Cameron M, Bob D, Captain Kirk's Jockstrap, Tony T Kites, Elmore, Craft Computing, Dr. Mrs, Spire, Zapf, Armakeel, Dale, Martin, Doom Crew Inc., Alma, Crash Doom, Sunburnt Cat, Cliff, Grurg, SKL, DBD, Zanforian, Dez, Zaish, Mike K, Renaud, Good Suck, Big Bird Tommy, Rusty Flute, Ad Hoc Law and His Chaos, Reagan, Sticks, Our Lady of Lemons, John Z, Paul, Dan, Zach, No K, No H, No Mercy, Danny Devoid, Some Horseplay, Period Clots, Cullen, Jack, RTB, Chris, Eric, Tactical Possum, Marcy Level, Ergay, Cameron O, Shardalos, The Monk, Rhiannon 99 and Urch, Alex, Brad, Stormby, Kevin, Igerbox, Transrights, Jean Baptiste, Daniel, Talon, I Don't Know What I'm Doing, Aaron, Roger Pangome, and not the Sirloinka, not the Filetka, Joseph Ribka. Thanks for watching, and you'll see more mind-melting filament frippery in the future!